This is Concept 2 notes, and now we are going to dive deeper into ionic bonds. We're going to learn how to draw representations of them, name them, write the chemical formulas, all of that jazz. Now, these notes are longer, but just know if we were in class and are in class together, we're going to chunk these up over several days and just do little pieces at a time. But for the sake of the video, I'm just going to do it all at once. There's also a lot of built-in practice, which I'm going to skip in the video, but I do want you to actually do it in your notes so that then we can go over it, when we're together in person or whatever. But I'm going to skip it in the video just so that you don't just write down all the answers and move on. I want you to actually try all of the embedded practice, okay? So, bringing up this picture again and a few little reminders on these first few slides. This should all be reviewed, probably the first 5 slides we're going to cover, okay? Ionic compounds are made of positive and negative ions that chemically bond in a way that the charges on those ions are going to equal out. Remember, ions are charged atoms. Cations are positively charged because they have lost electrons. This is typically metals. They have a lower electronegativity, so they're not going to attract those electrons as much, and the other one's going to take them. The other one is an anion, negatively charged because they gain electrons. These are typically nonmetals that have a higher electronegativity, so they're going to attract those electrons stronger and take them. Remember, ionic bonds are formed in chemical reactions when E are transferred from the atom with the lower electronegativity to the higher, because electronegativity is the ability of an atom to attract electrons in a bond. So anions have that higher electronegativity, and cations have that lower electronegativity. So we can predict the type of ion an element will form just by looking at where it's located on the periodic table. So looking at lithium, it's in group 1, it has 1 valence electron. It makes more sense for it to lose that 1 than gain 7. So it's going to lose that 1 to become stable. When it loses an electron, it's getting rid of negative charge. So now it has a positive charge and it becomes a cation. And we would write this as lithium 1+. That would be the notation for the lithium ion. Okay? What ion would nitrogen form? Here's another example. Well, nitrogen is in group 15. It has 5 valence electrons. So it needs to gain 3 in order to be stable and have that full outer energy level of electrons. And when it gains 3, it becomes an anion with a -3 charge. And so we write it as N3-. And I know this is kind of weird, why is the minus sign after the number? Honestly, I don't know the reason. I just know that's what we do in chemistry, is that we do 3- as opposed to -3. So just know that's the proper way to write it. So elements in the same group, this is going all the way back to unit 2, the atom, but we learned that elements in the same group have the same number of valence electrons. And because of this, elements in the same group tend to form ions the same way, and thus tend to form similar types of bonds. So example, all elements in group 1 have 1 valence electron, so all of them lose 1 to be stable and form a cation with a 1+ charge. Like we said, lithium will be Li1+, sodium will be Na1+, potassium will be K1+. Now, another slide that you've seen before, you saw this at the end of our Unit 3 electrons when we were looking at periodic trends, is oxidation numbers. Now, an oxidation number or an oxidation state technically represents this general distribution of electrons among bonded atoms in, a compound or a molecular compound or a polyatomic ion. But they are often synonymous just with the charge of an ion. That's not always the case, but it typically is. So for our purposes now at this point in the year, I just want you to think of an oxidation number just being the charge of an ion when it's within a compound. And we write them as that superscript in the upper right-hand corner of the symbol. Remember, all the group 1 elements have 1 valence electron, so they're going to form an ion with a 1+ charge. Group 2 will form 2+ because they're going to lose those 2 electrons to be stable. Now, transition metals, groups 3 through 12, they can kind of transition and have different, oxidation states. And so we're going to skip those for now. Group 13 are going to be the 3+. Group 14 have 4 valence electrons. So it's typically just as easy for them to gain as it is to lose. And so really what we do see with group 14 is they don't actually typically form ionic bonds at all. They form covalent and share. We'll get to that later. Group 15 have 5 valencies, so they have a 3 minus charge. 16 have 6 valencies, so they only need 2 more to be stable, so they'll gain 2 electrons and have that 2 minus charge. Group 17 will have that 1 minus charge. And then group 18 would have 0 charge because they're not going to do this. Now, what we should see in a compound when we're looking at a chemical formula is that even though the cation has a positive charge within it and the anion has some sort of negative charge, overall, the charge should be 0. The compound should be neutral. And that goes along with the rule of 0 charge, which states that the charges of metal cations and nonmetal anions should always add up to 0. This makes the overall compound neutral with no charge. Okay, so for example, this picture represents the rule of 0 charge. If aluminum and chlorine are going to form a bond, aluminum has 3 valence electrons it needs to get rid of. So if it only bonded with one chlorine and made AlCl, 1 and 1, then that chlorine would be stable, but this aluminum would not. It would still have 2 valence electrons. It needs 3 chlorines to bond with in order to be stable. And so when aluminum gives up these 3 electrons, it becomes Al 3+, and then it makes 3 chlorines that have a -1 charge because they gained that extra electron. And so the overall compound is AlCl3. And this should look very familiar. We did an inquiry activity in class where you learned how to draw these Lewis structures for compounds to help visualize how the compounds and these bonds form. And so we're going to write in our notes the step-by-step process for how to use these Lewis structures to show bond formation. But this should all be a refresher because, again, we did an entire activity on how to do this. But I know sometimes you guys don't feel like you were taught something unless it's in your notes. So we're going to put it in your notes, okay? So to use a Lewis structure to show bond formation and to help you determine that rule of 0 charge, like how many it would take of each atom in order for the overall compound to have 0 charge, drawing these Lewis structures can be really helpful. So here's how you do that. You draw the Lewis structures for the individual elements, like what we just saw. You draw one for aluminum, you draw one for chlorine. Then you use an arrow to transfer electrons from the metal to the nonmetal. Because again, or just whatever has the lower electronegativity to the one with the higher electronegativity. And then you're going to add elements as needed. Like once you drew that 1 electron from aluminum to chlorine, you saw that the aluminum still wasn't stable. So we needed to add another chlorine in order to transfer another aluminum. And so you'll keep doing that until both atoms are stable. And you may have to go back and forth a little bit. Then you're going to draw the new Lewis structures after the E have been transferred, showing the charges of the atoms like we saw on the right side of the last slide. And then you can write the chemical formula using subscripts to show how many of each element were needed. So the last one would have been AlCl3. And then the last thing we always want to do is just double check that the overall charge is 0. If the overall charge is 0, you know you did it right because that's what we should see when we create these compounds. Okay, so let's do 2 examples together. So what compound would form between magnesium and bromine? What would we expect to form? Well, let's go through our rules. First, we're going to draw the Lewis structures for the individual elements. Magnesium is in group 2, so it would have 2 electrons. Remember, we draw them all on their own before we pair them up. Bromine is in group 17, so it has 7 valence electrons. Okay, so we would put 1 on each side before we pair them up, so we have 1 free here. Next, we're going to transfer E using an arrow from the metal to the nonmetal. So from magnesium to bromine, this would come and pair up here. Now, step 3, we're going to add elements as needed until everyone's stable. So right now, bromine's stable, but is magnesium? No, it still has this random electron it needs to get rid of. So we need to add another bromine. When we do that, now bromine has 8, each one does, and magnesium, it appears like it has none, but it would just kind of go to that next innermost layer. So we can do the last step, which is we draw the new Lewis structures. So Mg would have a 2+ charge because it lost 2 electrons. And then we would draw 2 bromines. Each one has a -1 charge. And remember, you never technically have to write a 1. If there's, ones are understood. So if there's nothing, it's just understood that it's a 1. And then step 5, we can write the chemical formula. So there's 1 magnesium and there's 2 bromines. So we would expect it to be MgBr2. And then last but not least, just double check that the overall charge is 0. So think, Magnesium has a +2 charge. There's one of them. Bromine has a -1, and there's two of them. So -1 plus -1 gives me -2. With the +2, that gives me an overall charge of 0. All right, let's do one more before we practice. What compound would form between aluminum and oxygen? All right, well, aluminum is in group 13. It has 3 valence electrons then. Oxygen is in group 16, so it has 6 valence electrons. So we start transferring those electrons over. So we would do 2 to this oxygen, and now that atom's stable, but aluminum isn't. So now we got to add another oxygen. All right, now we transfer that. Yay, aluminum's stable, but is oxygen? No, it still has this one that needs a pair. So we got to add another aluminum. We transfer that. Now oxygen's good, but again, aluminum's not. Got to add another oxygen. But then when we get to here, we see, oh yay, everyone is now stable, so we can rewrite them. We have 2 aluminums, each with a 3+ charge. And then we now have 3 oxygens, each with a 2- charge. So that's 6 positive, and this is 6 negative. That gives me 0 overall, which is what we want. So it would be Al2O3 is what we see here for the chemical formula. Okay, now I want you to try this on your own in your notes. I want you to do aluminum and nitrogen, strontium and fluorine, and magnesium and phosphorus. And then we are going to pause and do a little activity where we're going to model ionic compounds so you can help visualize this a little better. But for the sake of the notes, we're going to move forward and start talking about nomenclature. So all compounds have chemical formulas which represent the number and types of elements that are in each compound. And then they also have names so that we don't have to refer to that as AlCl3. It's aluminum chloride. Okay, so there are different naming rules that we're going to use for different types of compounds. So there are the binary ionic compounds, which are compounds made of just 2 different elements, like MgCl2, AlF3, and they are going to transfer E in an ionic bond. So those have their own set of rules. And then we've got the ionic compounds that have polyatomic ions in them. A polyatomic ion is a charged group of covalently bonded atoms, but it has a charge, so that's why it forms an ionic bond. And then we also have binary molecular compounds, which are compounds made of 2 elements that share E in a covalent bond. Now, there are also acids. There are also molecular compounds that are not binary that we could learn how to name, but we are not going to do that in this class. We're just going to form on these 3 categories. Honors, we will learn how to name acids, but everyone else, we're just going to learn these 3, and we're not going to learn anything more complex than these. Okay, so first, let's learn how to determine the chemical formula for a binary ionic compound. So you can do what we just did. You just did this. You determined the chemical formula. When we did that with Al and Cl, aluminum and chlorine, you figured out it was AlCl3 by drawing it. But you may not want to draw it every single time. Okay, so what you can do is you can take the name, the chemical name, and we can use it to write a chemical formula. And I'm going to teach you how to do that right now. So first thing you do is you write down the ions of each element with charges. So you write down the symbol with the superscript that has its charge, okay, or the symbol with its oxidation number. Then you're going to determine the number of each ion it's going to take to make the overall compound have 0 charge, because remember, that's the goal. And so we call this, or I call this, I shouldn't say we, this is something I call it. I refer to this as we're going to crisscross applesauce those charges. Then you write down the formula using the subscripts to show how many of each ion it took. And then you are going to reduce or simplify if needed. Okay, so if you see that it's a 2-to-2 ratio, you're going to simplify that down to 1-to-1. Because remember, the chemical formula for an ionic compound is showing the ratio in the crystal lattice. And so we want it to be as simple as possible. Okay, let's do an example. It'll make way more sense in an example. Okay, first, what would be the formula for the compound that forms between calcium and nitrogen? Well, first, step 1, write down the ions with their charges. So calcium is in group 2, so it's going to most likely form a 2+ charge. And then nitrogen is in group 15, which typically have the 3- charge. Okay, step 2 says determine the number of each ion it's going to take to make a compound with no charge, aka crisscross applesauce. So what I mean by crisscross applesauce is we're going to take this charge on this ion and we're going to put it here to be the subscript, and this one and put it there. So that 2 is going to go over to the nitrogen, and that 3 is going to go over to the calcium. And then step 3, we're going to write down the formula with those subscripts. So it'll be Ca3N2. So that 3 came from the nitrogen, the 2 came from the calcium. And then we will reduce if needed, but 3 to 2 can't be any simpler. We're not going to cut it down to calcium 1.5 and nitrogen 1. That doesn't make any sense. We're not going to do decimals or anything. So this is as simple as it gets. And then lastly, you just want to double check that rule of zero charge. So again, 3 calciums times 2 positive gives me 6 positive. 2 nitrogens times 3 minus gives me 6 negative. Well, 6 positive and 6 negative will give me 0 overall. Okay, so I want you to apply these steps and try them for these 5 problems, and then we will go over those in class. Now, the next thing we want to be able to do is go the other way with these binary ionic compounds. If I give you the formula, I want you to be able to tell me the official name, not just say aluminum and chlorine, because that's not actually what it's technically called. Okay, so here's how you do this, and this is actually a lot easier. First, you'll just write the name of the first element, which is, your metal typically. And then you're going to write the name of the second element, the nonmetal, and you're just going to add an IDE ending. That's it. Okay, so look at an example here. CAS. Okay, looking at CAS. Well, first, name the first element. So Ca is calcium. And then second, name the second element, which is sulfur. But we're going to add an IDE ending. So instead of sulfur, we're going to say sulfide. Okay, so the answer is calcium sulfide. I know this is tricky because you might think, why wouldn't it be sulfuride? Well, usually you kind of take off the N and then add the IDE. And you'll get better at these, I promise, and you'll become more familiar with how they sound right. Okay, so now I want you to try to do this. I want you to take these 3 chemical formulas, or 5, and write the names using those rules. And then again, we're going to stop and practice this. This is where we'd be breaking this up into multiple days, but for the sake of the video, we're going to keep going. All right, now, we know it can't be that simple, right? It's always going to be more complicated. So we're going to look at some exceptions to these rules. And you may remember when we did our modeling ionic compounds activity with the blocks that you might have been introduced to that term polyatomic ion for the very first time. And so now we're going to learn about 2 different exceptions to the rules we just had. We're going to learn about when there's a polyatomic ion and then when there's a transition metal. Okay, so just a reminder, what is a polyatomic ion? It's a positively or negatively charged, covalently bonded group of atoms. And there are a ton of these. There's a whole chart, but they're very common and they have special names to represent them. So ammonium represents NH4 with a positive 1 charge. SO4 with a -2 charge is something called sulfate. And you will not have to memorize these if you're in my class. I will give you a reference sheet with all of these on them that you can always refer to on the test, okay? But these are their special names and these are the ions' special formulas. So now let's look at the rules that we've already written and we're going to add on to them. Okay, so I'm going to add on the polyatomic ion special rules in light blue to the rules we already learned. So we're going to start by going formula to name because I think that's a little bit simpler. Okay, so just like always, you would name the first element, but here's the exception. If the first element is actually a polyatomic ion, you'll use its special name. So instead of saying calcium, if it was, ammonium, you would use ammonium. So you're just going to use its special name. And then, same thing with the second. Instead of doing the second element with an IDE ending, if the second element is a polyatomic ion instead, you just use its special name that you saw on the chart. Sulfate, chlorate, carbonate. You don't add an IDE ending. You don't change it. You just use the name as you see it. Okay? So examples, let's name these. All right, first we see a metal, so we just name the metal, sodium. And then next we see a lot of letters. Usually when you see a lot of letters, you just think that's a polyatomic ion. All right, so right here, this PO4, look it up on your chart. That's phosphate. So this first one would be sodium phosphate. All right, this next one, Mg represents magnesium. SO4, if you look on your chart, is sulfate. So this is magnesium sulfate. All right, now we see NH4. Okay, that's a polyatomic ion, so it has a special name, ammonium. And then we end with Cl, chlorine. So because it's just a normal element, not a polyatomic ion, we add that IDE ending. So ammonium chloride. Okay, so while you're in a pause, I want you to do these 5 to practice that. For the sake of the video, we're going to keep trucking. So now let's go the opposite direction. How do we go from the name then to figure out the formula? And so same thing as before, same exact rules. I'm just going to add some additional tidbits in the light blue to represent what we do for the exceptions when we have these polyatomic ions. So first, you would write down the ions with their charges. But my recommendation here is when there's a polyatomic ion, write it and put it in parentheses. Okay, so that you remember that you're not going to mess with anything in the parentheses. You can't change the subscripts or anything that's in there. You cannot mess with it. So put the parentheses there as a little barrier for yourself. And then same thing, we're going to crisscross applesauce, but we're going to do everything on the outside of the parentheses. You cannot change anything inside the parentheses. So sulfate is SO4. If you change that 4 on sulfate, it's no longer sulfate. Okay, so you cannot mess with it. You only change things on the outside. And then we just write down the formula with the new subscripts and we would reduce if needed. Okay, let's do an example of this one. All right, what would be the chemical formula for a compound of calcium phosphate? So first, you write the symbol with their charge. Calcium is Ca with the 2+ charge because it's in group 2. Phosphate, look it up on your chart. It is PO4, and that entire thing has a -3 charge. So we put parentheses around it to protect this whole group of atoms has a -3 charge. So now when we crisscross applesauce, we're just going to go on the outside here. So the 2 is going to go to the outside of the parentheses. The 3 is going to go there. We rewrite it. It's calcium 3. And then this whole thing, PO4, that whole thing gets the 2. And again, you can double check. 3 times +2 gives me +6. 2 times -3 gives me -6. +6 and -6 give me 0. And then we meet that rule of 0 charge. And here are some more that you can practice, and we will go over in class. And then we're going to do similar practice to what we just did earlier, but we're going to do it with those polyatomic ions mixed in, so you can remember those. All right, there's one more exception to our rules for ionic, and that is transition metals. So this is exception number 2. These are metals that transition because they form many different ions. Like magnesium's always going to form that +2 charge, but the ones in the middle of our periodic table can get a little funkier. So again, sodium is always Na1+ because it's in group 1, and group 1 metals have 1 valence electron, and so they're going to lose 1 electron to be stable. Iron, though, is like a transition metal. It can be iron with a 2+ charge or iron with a 3+ charge. It just depends. So because of that, we can't just like look at the periodic table and know the charge that iron's going to form. We don't know that. And so when we name chemical formulas with transition metals, we have to include something to tell us what the charge is, or else we won't know because we can't look it up on the periodic table. And so what we include is a Roman numeral. That is what we use to show this. So for example, if I wanted to copper 1 is the same thing as Cu with a 1+ charge. Copper 2 is the same thing as Cu with a 2+ charge. And so that's what we're going to be using moving forward. Okay, so let's look at our rules again. Same thing, I'm just going to add to our rules with purple text what applies to naming these with transition metals. Okay, so exception number 2, if the first element is a transition metal, you're going to include a Roman numeral to indicate the charge of the metal. And then if you're going to name the second element with its IDE ending as normal. So that's not going to be affected at all because the second one's just going to still be a non-metal, right? So it can't be a transition metal. All right, so let's do some examples. CuCl. So we have a copper, and now to figure out its charge, you kind of got to look in reverse. Okay, so remember, the number right here came from the charge of chlorine. So there's 1 copper because that came from the chlorine ion. There's only 1 chlorine, so that came from the copper if we reverse crisscross applesauce. So this must be copper 1 chloride. Whereas here, the 1 that's on the copper, remember, that came from chlorine because we crisscross applesauced. The 2 comes from the copper. So this one is actually copper 2 chloride. So that Roman numeral represents the charge of the metal, not how many there are of the metal. It represents the charge of the metal. That's really important. So again, how do we figure these out? Because this is hard. Like, how do we do this? What did I just do? I reversed crisscross. That's your first option, is just to kind of do that reverse crisscross applesauce. Another option that's a little bit more complicated but is foolproof is to use visuals or math to determine what charge the cation must have for the overall charge to be 0. And no matter which way you choose, just always double check your work. That's the thing. You can always go backwards and use this and then go in reverse and do the chemical formula, and you'll know if you got it right or not. Okay, so let me model how you can do this. So let's do another example. Option number 1, look at this chemical formula. Okay, so we know that this is tin, and this is the polyatomic ion phosphate, but I don't, tin is a transition metal, so I've got to put a Roman numeral to indicate the charge. So I don't know the charge on tin. I do know the charge of phosphate is 3 minus, excuse me. So that 3 is what went here. That means whatever tin's charge is what went on the outside over here. So this must be tin for phosphate. All right, let's do another option. Same thing, let's look at an example. So look, we have 3 tins in this compound, and we have 4 phosphates that all have a -3 charge. Okay, 4 times -3 gives me -12. That means 3 times whatever this question mark is must give me +12, so that the positive and the negative overall make 0. And so that's where we can also figure out that that must be that +4, so it's tin for phosphate. Okay, this will get easier with practice, I promise you. All right, so here are 5 that you can practice. And then, of course, we'll do some practice, more practice in class. And then we also have to talk about going the other direction. So how to determine the chemical formula for an ionic compound with transition metals. So going from name to formula. This is easier to me. So the first step, the only new thing here is the transition metals charge will be given by the use of Roman numerals. So if it's a Roman numeral 3, it has a 3+ charge. Or if it's a Roman numeral 2, it has a 2+ charge. It's always going to be positive because the metals are always cations. And then you do your crisscross applesauce, write down the formula, reduce if you have to. Okay, so let's do an example. What's the formula for the compound iron 2 oxide? Okay, so you just write it down based on the charge. So if you looked up iron on the periodic table, you'd see it's Fe, and you'd see it's a transition metal, so you don't know what the oxidation number most likely is. So you'd go ahead and look at the Roman numeral and say, oh, it told me it's a 2. So iron 2+. Oxide is referring to oxygen, which has a -2 charge. Now I'm going to crisscross applesauce, so this 2 goes there and that 2 goes there. I get Fe2O2. But wait, is 2 the simplest that could be? No, we have to reduce. So really we'd reduce those down to 1 to 1, and the answer is FeO. And you can double check. 1 iron with a +2 charge and 1 oxygen with a -2. +2 and -2 give me 0 charge overall. So it hits our rule of 0 charge. All right, here's some of these for you to practice. And again, we'll do even more practice with these transition metals. And now just to kind of wrap this up, I just want to summarize everything we've talked about all in one spot. So let's do a summary of all the rules in one spot. So going from formula to name. First, you name the cation, which is the metal. Exception number 1, if it's a polyatomic ion, use its special name. Exception number 2, if it's a transition metal, you got to include that Roman numeral to indicate the charge of the metal. Then you name the anion with an IDE ending, but if it's a polyatomic ion, you use its special name. Okay, let's refer to those summary rules. I want you to try 3 more practice problems, and then let's go through the opposite direction. So summarizing, putting it all together. When we're going from name to formula, you write down the ions with their charges. You crisscross the charges to determine the subscripts, or crisscross applesauce. You write the formula with subscripts. You reduce and simplify if needed. And here are a few more that you can practice doing. And then last, I just want to hit you with some helpful hints to kind of take away when doing this. So when determining the Roman numeral for a transition metal, try to do that reverse crisscross method first. And if the subscript doesn't match the charge of the known non-metal, it must have been simplified. So that's a good sign there. So when it doesn't match, it's easiest if you just kind of do a little trial and error and just double check your work by going the opposite direction. Again, take your formula, go backwards, and figure out the name or vice versa, and just see if your results match. And that'll be a great way to double check. And I cannot say this enough. Always put parentheses around your polyatomic ions so that you can protect them. Protect the polyatomic ions with parentheses, PPP, okay? Remember, you cannot change the subscripts of the polyatomic ions, or else it changes their identity. So those parentheses help you to remember to protect them so that you don't mess with them. All right, that was a lot. We're going to practice this tons and tons. Don't worry, and we'll start with this.